Brian, you here? Brian, are you here? Brian, are you here? Brian, 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 Brian?
Oh yeah.
No, well, you don't have to, but do you understand the C code on the left side right here? You should, right?
No, I don't.
Oh, let me go over it. I think once I go over it, I should be. So I'm defining x to be. I'm declaring x to be int 8, right? Whatever. This is just a type of data that I'm declaring, and then I'm assigning 8 to x, and then I'm calling uh the function f within f, right? So basically, let's work our way in, right? So basically, inside this function, I'm calling f as an argument, and once the program steps in, what's gonna do is it's gonna look at this, right? And it's like, oh, okay, I'm calling f as an argument, right? And f as an argument has 2, and x minus 2 as an argument, right? So what's gonna happen is it's gonna call f, and then 2 is gonna go as an argument, as a parameter into f underscore x, and x minus 2 is going to be going as a argument into f minus y, right? So what that means is x is 8, so basically 2 is going to go into f of x, so 2 times 2 is going to be 4, minus, now it's going to be 8, now it's going to be, since 8 minus 2, so that's blah, 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 what's that? That's 6. So it will be 4 plus 4 minus 6, right? So again, negative 2, right? So basically, now this thing now became, this is now negative 2, right? This is the value of negative 2. And then after it passes this function, it's going to come out again, and it's going to call f, and now this time it's passing x as the first parameter, and then negative 2 as the second parameter, and then so it will be
So
x
it
is
keeps
8.
going and going with new results.
Huh?
So it just keeps going and going with new results.
It has results. What do you mean?
No, like
There's
it'll
no
get
loop here.
yeah, it'll get a new result and it'll plug it in and it keeps going and going.
No, there's no loop here. That's it. It just gets the function, and that's it. It returns. You see the return one right here?
Hmm.
That's it. And once it calculates, it returns, and it comes out here, and it gets assigned, and then it goes in, and then so once it gets past like this this subroutine, this function, and then it calls the function again, and then it's all getting assigned to x. There's no loop here. There's no loop here, so it's good. But then so 8 gets in here, 8 goes in here, 8 times 2 is freaking 16, minus negative 2 is 18. Basically, we need it. Basically, if this is the function, we'll get 18 as the assignment, right? So, so the so the test tomorrow, the final project tomorrow, quote unquote, the 24-hour project that we're working on is he's gonna give us a C code like this, and he's gonna give us a faulty assembly code on the side like this, right? And then basically we want to fix these and put notes. This is the correct version. I typed this out, and the correct version. And then basically you want to type and replace different assembly instructions in order to match what it's doing in the C function, in the C code, right? So um, I'm not gonna. You don't have to listen if you don't want to, but I'm just gonna talk out loud because it makes sense. So to go down, um, we want to use the instruction no op. So that's specifically for the command line. If we want to run this in command line instead of running in the logicin, but it doesn't matter. The second line is clear D. We had to change it just because there's no such thing as clear as our opcode as in the assembly language that we're using. So there's no clear code, but we want to initialize D to 0 because D is our conventional stack pointer, right? We want to point it to 0, and then we want to add jump main just because our label F is up here, because C is a higher level programming. It immediately knows that it's gonna go into main, and then it's gonna read this and it's gonna call the subroutine the function. But assembly doesn't know that. So basically, what I had to do is, if we can have put main, like this main label, we could have put it before F, and that's completely fine. But since we didn't do that, we had to add the label jmpi main, so then we can basically skip over F and go into the label main, right? And that's what this is doing. It's basically skipping the whole F function. because we're not doing f first. We need to go in the main and then we call f, right? So then we'll go straight into the f function now to fix it. This looks right. This wasn't this was changed. This was right here. Yeah. So it's return address equal to 0. There's no assignment like that syntax in the opcode. It's a semicolon. So we're basically assigning the constant 0 into the return address. We had to switch the f underscore x. Basically, these two parameters, f of y and f of x. We switched it over just because when we're in assembly, we go from the rightest most parameter into leftmost. So the rightestmost has a higher address, right? What I mean by that is if you look at like a stack, this thing is higher up. It has a higher address compared to this one. So basically, if you call this address, this won't be if you call the stack pointer right now, this would be the first one to show up without offsetting anything. So that's why I need to change it, because right now it's at this point, this would be f of y, then f of x. But that's not it. It's, if it's f of x and f of y, that's why we're going to swap it, and f of y is last, then f of x, then the return address. Because whatever is last is going to be used first in the stack pointer, right? So next we go down and assume that the labels are correct, and then we load the parameter f of x into the register C. And we had to change that immediately just because f of x is not being we don't need to offset because f of x is already being pointed to by the stack pointer, right? Because we didn't change anything. So when you load f of x, we don't need to offset anything because the stack hasn't changed. So we don't need to offset to get f of x, the return address. So then after that, they didn't have the line, so we had to insert this at CD. Basically, adding the register to the stack pointer will get me the address of this variable, and then using the syntax was wrong in this one because the parentheses is supposed to go on the second operand, so that's why I changed it. But basically, what that does is we force C to basically dereference C, and now we got the value of C from the address of C, right? So whatever was at the address C, now we got the value of C, right? So whatever x is, f of x is, it's 2 in this part, then now C has 2, right? So we keep on going down. This was a block of code that was incorrect, and this was where it was. This was the incorrect code, and this is just saying that we're copying a register from D to C. So we're copying the stack pointer of D into register B, right? Which is fine. And then we incremented B. So then basically, our stack pointer is now at register return address, right? That's what it says right here, return address. We increment B, right? Remember, f of x and f of y is higher address than return address. So when we increment B, that means it goes up by 1 byte. When it goes up by 1 byte, that means it gets the address of f of x. And then increment B again, and then goes up another byte. Now we got f of y. So that's why, in the beginning, I said that f of y is a higher parameter address than f of x, which is also higher than return address. So, incrementing B both times will get me the address of f of y, but we don't want the address f of y, right? Because we want is the value, so we can do the arithmetics here, 2 times f of x minus f of y. So we need the actual value, and to do that is we force B, same thing as we did up here, loading the same register into another one with dereferencing the address of f of y into B. So now we actually have the value of f of y, and then we subtract B from C, right? But then we know that B is actually the value of f of y, and C is the value of f of x. So basically, what this instruction is doing is saying that, oh, I want B to be equals to f of y minus f of x, or fx. That's not what we want to do. We want 2 times fx minus fy. So so these things have to be swapped and stuff like that. So that's the incorrect one. And then instead of just changing it, I did this here. So basically, what we did was, first things first, we want fx times 2, And all we have to do is just add C and C, right? When we do that, basically we're just adding one to another. So that's basically multiplying it by 2, because you're just adding it together. So you're adding whatever value is. It might be 2. 2 times 2 is 4, and no, 2 plus fucking 2 is 4. So you just add C and C. So now register C is the value of 2 times f of x. This part we can leave, because this part was right. This whole section right here was because we wanted to get we got the address of B, or the stack pointer, and then increment the stack pointer all the way to address f of x, got the value of ffy, and then what's happened is down here is we changed the subtraction instruction to C and then B, right? Because the subtraction is basically its subtraction is x is equal to x minus y, right? So that's what the thing is. So we want the actual value to be in the register C. So now we changed it, and we actually have, and C is 2 times fx. So now C, so this instruction is basically saying that we're taking 2 times fy, 2 times fx, which is the value that we got from here, right? It's still in register C, and minus the value of f of y, which is in register B, right? And now it's actually, once you've done this, right? Based on this instruction right here, we know that C now holds the value for this arithmetic operation, and we want to copy the register, the value of C into the register of A, and now and register C is empty. We don't need register C anymore, and so we always want to it wasn't included here, but I needed to insert this because we want the return value to be in register A. That is just a convention thing for this language. Like for this language, we want A to be the return value and the scalar register, and D to be our stack pointer. But that's just a convention thing. So you can put this into B if you really want to, but that has nothing to do with logical stuff. Going down here, right here is LDCD, syntax error. We do need the brackets. That's just the syntax. We need to increment D here. We need to increment the pointer because we want to deallocate the stack, right? Basically, now we reserved the stack right here. We were using the stack to calculate all that stuff because we deallocate the stuff, and now we need to actually oh, did I freaking forgot to actually forgot to deallocate. Okay, so this is deallocating the stack, reserving, insert it, allocating space for allocating space basically for fx. And so since I deallocate the stacks, since it went down one, I need to bring this back up. So then basically the stack is quote unquote balanced, right? And jump C is basically returning to the caller, right? Returning to caller. Basically, this is gonna, after this whole thing is finished, I'm going to return to the main being the caller, right? So that's how we implement and fix the function f. Now going down to main's a little bit bigger. So first things first, return address. There's no such thing as a return address for main because main is not being called by anyone, right? The main return address is for callees, not the caller. So there's no one calling main, so we can delete that. So which means we have to change the constant for the main x, being this is the local variable. This is the byte location. We need to change it just because this is at the 0th byte for this invocation frame. This is what we're using, right? So then we need to. Oh, you know what? I don't. I don't think I need. No, I don't think I need this right here. I don't think I need to deallocate, not only a decrement D, just because the fact that main is doing the decrementing right there. Yeah, main is decrementing for us, so we don't need to do that here.
Oh yeah.